here we go. We are going to find homes for those electrons, and we're just basically going to build on what we did in part 4. So actually, what I'm going to build it over here again. We already did a couple of electron configurations. All electron configurations are basically saying where the electrons are. Okay? So this is going to help. I'm going to basically rebuild over here what was over here before. So when n is equal to 1, we said there's one type of subshell. It's 1s, and any s type has just one orbital, right? When n is equal to 2, there's 2 subshells. We have a 2s, 1 orbital, and a 2p, 3 orbitals. And I think I'm going to go ahead and start connecting my orbitals. We'll try that. So basically I made a rectangle, and I'm going to put a couple of lines there to make my 3 orbitals. And when n is equal to 3, we have a 3s, 1 orbital. We have a 3p, 3 orbitals. And then we have a 3d, which is really exciting. I get to do 5 orbitals, right? 1, 2, 3, 4, 5. Yeah, I like that. And when n is equal to 4, and this is where I'm going to have to actually revisit this. I told you guys this is increasing energy as I kind of go like this up the board. I'm going to have to revisit this, but for now I'm going to put 4s, 1 orbital. I'm going to make them kind of small. 4p, 3 orbitals. 4d, 5 orbitals. 1, 2, 3, 4, 5. I like it. And then 4f. How many orbitals does 4f have?
7.
7, yeah. Oh my goodness. 1, 2, 3, 4, 5, 6, 7. Okay.
Yay.
Yay. Okay. So I said we already done electron configurations. For instance, if we pick on helium, helium's atomic number 2. It's got 2 protons. How many electrons around a helium atom if it's neutral? 2, exactly. And so actually that is the electron configuration for helium. Isn't that adorable? Okay. It's a wonderful thing. Actually, we see the word ground state here. Basically, ground state is finding the lowest available home. Okay? And that's definitely for helium. So ultimately here, and this is where I kind of need to switch things up here. Okay? I'm going to have to switch things up here in that as I've drawn this kind of simple n is equal to 1, 2, 3, and 4, and kind of various subshells, this is not really how they are with regard to energy, the subshells. Basically, the subshells are going to do kind of a scramble, a little bit of a scramble at the upper end here. And that's according to what I call the lowest n plus L rule. So n's are obvious, right? N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Well, what the L part actually is the orbital type. So also yesterday, or I should say on Monday, we talked about the different orbital types. We said there's the S type, there's the P type with 3 orbitals, there's the D type with 5 orbitals, and there's the F type with 7 orbitals. All right. They look better than my other boxes, I think. So the lowest n plus L rule, well, there's the n. Well, what the L part is this. And actually, in order to, the lowest n plus L, you're like, well, what are we adding? You know, the n plus. What's the plus part? What are we adding? Well, we need to put values for, L values for these. So the L value, like you see here, the L value for S is 0, and then it goes up from there. The L value for P is 1. The L value for D is 2. The L value for F is 3. Okay. And we said, although we won't have to mess with it, we said that actually beginning where the principal energy level n is equal to 5, you know, we end up picking up a G type subshell. We aren't going to have to worry about that. But the value for G would be, not so surprising, 4. The value for H would be 5. Okay, so here's how N plus L works for a given subshell. So for each subshell, we can calculate an N plus, these are all subshells, right? For each subshell, we can calculate an N plus L value. Okay. So you kind of see here, N is equal to 1, we have 1s. Okay, N is equal to 2, we have 2s and 2p. N is equal to 3, 3s, 3p, 3d. N is equal to 4, we don't have up here. But my point is we can come up with, and I'm going to write it right here, an N plus L value for each of these. Do they look like subshells? They're subshells. Each one of these subshells, we can come up with what's called their N plus L value. So here it would be 1 plus 0, right? 2s. N is equal to 2. If it's an S type, that has an L value of 0. Okay. 2p, N is equal to 2. And if it's p, the L value is 1. So that's 3. 3s, the N is equal to 3. The any S type subshell has an L value of 0. Okay. 3p, we have 3 plus 1. 3d, we have 3 plus 2. Okay, and you see where the 2 came from. Okay, from the D. Okay, so these are N plus L values of these subshells. All right, now, here's one of the things I bet you already see is actually we right away have 2 subshells that have the same N plus L value. And that's okay. I'll tell you how to handle that here in a minute. But let me go back. Okay. All right. I wanted to check something. So this is what I was checking for in that previous slide. So here's the deal. When we find homes for electrons, and electrons need to be in their ground state, the lowest possible energy, we're actually going to go with the subshell that has the lowest N plus L value. Now, some of you are familiar with something called an arrow diagram. I'm going to introduce the arrow diagram. But what the arrow diagram does is help you to see which is the next lowest N plus L subshell. Okay. So in the case we saw a minute ago where we had actually we have 2p and 3s both have an N plus L value of 3. If that's the case, what this is saying is we go with the first one to find homes for electrons will be 2p, and then we'll find homes for electrons in the 3s. And kind of it's like you might intuitively figure, we're going to fill it up, and then we're going to fill it up, and then we're going to fill it up, and then fill it up, and send it around. Okay, according to the N plus L numbers, though, which, like I said, I'm going to have to do a little bit of scrambling here on the way I've drawn increasing energy. So this whole idea of placing electrons first in the lowest energy and kind of going up to the next energy, the German word Aufbau means building up, and that's kind of what we're doing. It's called the Aufbau Method, which is kind of fun because, for instance, we found homes for the 2 electrons around the helium atom, and you're like, okay, the periodic table is kind of fun. It kind of skips across. So if you skip across after helium with 3 protons, and if it's neutral, 3 electrons, we lithium. So dang, all I got to do is, for lithium, do that. Okay? Not too bad. Kind of. So my point is you're kind of building up as you go. All right. So this type of notation, actually, this is called box and arrow that I have on the board, otherwise known as the hand cramp method. Okay. So a few things about this box and arrow. The boxes represent orbitals. Okay. So these are each orbitals. Of course, the arrows represent electrons hanging out in those orbitals. And like I kind of kid, but you will hear me call this the hand cramp method of showing electron configuration because you have to draw the boxes. One thing about this box and arrow notation, sometimes I have students that, for whatever reason, don't want to tell me which subshell it is. Okay, you have to tell me which subshell it is. Okay, you can't just draw the boxes and I'm supposed to guess. Okay, you have to give the N and the L value. The other one, hopefully then, is the non-hand cramp way. Okay, and it's called spectroscopic notation, just a different way of saying where the electrons are hanging out. You know, if you're talking about the electrons around the same atom, they're going to basically be the same. They're going to tell you the same information. This spectroscopic way of showing electron configuration, spectroscopic notation, it loses a little bit of information, and I'll kind of show you what that looks like here in a minute. But that's okay. So be able to kind of show how electrons are configured in both of those. Okay, so the box and arrow notation is what we're going to hit first. We've been talking about, we talked about orbitals. To me, orbitals are so cool because they not only kind of say the shape of the pattern of electrons that are associated with a nucleus, but they also have energy. They have a certain amount of energy associated with each orbital. Oh, before I move on, then sometimes this makes it to my test. Starts with the letter D. So when you see orbitals side by side, like any p-type has 3 side by side, starts with the letter D, what do we call those? Almost sounds like disparaging. What do we call those orbitals relative to each other? D. Yeah, degenerate. Degenerate orbitals. Degenerate. Okay, and actually that's going to be a player when we go to find homes for electrons, because one of the things I said Monday is that if you have 3 degenerate orbitals in a p-type subshell, 5 degenerate orbitals in a d-type, 7 in an f-type, they're all hanging out the same energy level. Okay, so when it comes time to placing electrons, I'm going to kind of show you how those electrons load, but you've got to fill that one before you go on to the next one. Okay, yep, so make sure that this says make sure each subshell is labeled. Okay. And I'm not going to torture you with this, but remember we talked about the Pauli's exclusion principle at the end of the slides in part 4, and we said it's the Pauli's exclusion principle is why if you completely fill a box, an orbital like we have for helium, it's Pauli's exclusion principle. That means one has to go up and one has to go down. The exclusion part is they have to be unique, and that's the last little bit that makes them unique. Okay. Usually the first to arrive actually has what we call a positive spin, so it's pointing up. But if you want to be a rebel, feel free to make it a downward spin. But if you put 2 electrons in any box, they better have, one better be pointing up and one better be pointing down. All right, so let's find some homes for electrons. Okay, this is the hand cramp method. Now, if I'm doing an electron configuration for anything, one of the first things you'll see on my answer keys, right out next to the element that I need to find how the electrons are configured around that, an atom of that type of element, I will write how many electrons I need to accommodate. So, of course, you guys have a periodic table. Hydrogen is atomic number 1. It has 1 proton, so if it's neutral, it has 1 electron. There you go. That's it. Helium, okay, does that. Okay, and these are all increasing, so we have 1, 2, 3, and 4 electrons. With lithium, we said already that lithium goes ahead and you skip to the next principal energy level, N is equal to 2. The lowest subshell is 2s, so only 1 electron there. And so for beryllium, we're going to go ahead and it's going to be like lithium, but we're going to add 1 more electron. And that last electron to be added is going to completely fill the 2s subshell. Oh. Yeah, not too bad.
If we were to add an electron to lithium, would it become beryllium?
It would become an ion. Adding or subtracting electrons doesn't change what. If you were to add a proton, to the nucleus of a lithium atom, it would become some form of beryllium. Yes. Protons, I know. Mess with it, right? Okay, so boron is atomic number 5, so the 5 electrons, okay, the first 4 go like lithium, so, no, darn it. The first 4 go like beryllium, and the next one goes ahead and goes into the next subshell. So you can kind of start to see how it's really important that you recognize that the S's can max out at 2, the P's max out at 6, the D's max out at 10, and the F's max out at 14. Yeah. So carbon is now our first example where we are ready to apply what's called Hund's rule. So remember I told you that these 3 boxes here, let me go ahead and do boron. Okay, so there's boron, right? That's cool. We're going to off-bow, we're going to build on boron, add one more electron. So here's the deal. These 3 are what we call degenerate, right? We have one more electron to find a home for. Now, the thing is, we're not going to buddy up, and it's almost like if you have a house with multiple rooms and multiple children, if possible, each child's going to have their own room. That's Hund's rule. Okay? They're degenerate orbitals. And again, it's Hund's rule. It basically says that last carbon, that last electron to be added, that 6th electron, it's not going to buddy up in the first orbital. There's 2 other vacant orbitals. It's going to stay what we call unpaired. It's going to stay unpaired if possible. That's it. Okay? And that's the first place where Hund's rule starts. So again, it's a classic to add on that section where I have vocab. So Hund's rule deals with electrons finding homes. Basically, electrons want to be unpaired if possible. So the example with carbon, we saw that we could go ahead and put that 6th electron in the middle p orbital, 2p. Okay? To make 2 unpaired electrons in the 2p subshell. And notice that if you go back to the example, they were both pointing at the same spin. Okay? So, in other words then, just to kind of make sure we're on the same page, paired electrons, okay, in this example for helium, these 2 electrons are paired. These are paired electrons, okay? This example we said for lithium, we need to find homes for 1 more electron. That is an unpaired electron. So your pairs, your kids want to be unpaired, your electrons want to be unpaired if there are degenerate orbitals available. Unpaired if possible. So let's go after carbon. After carbon is nitrogen. So let's go ahead and jot down what carbon was. So we said carbon was this. Okay, those are the 6 electrons around a neutral carbon atom. We need to find homes for 1 more electron, or a home for 1 more electron. How many people think it's going to go in that last box? Me too. Exactly. Perfect. Again, a little bit of a hand cramp, but just take your time. You should have time on your test when you do box and arrow notation. Of course, you'll have time at home to do the boxes right and to say under the boxes what subshell they are. Okay. All right. So oxygen, I'm going to go ahead and, so it needs to find homes for 8 electrons because there are 8 protons in the nucleus of an oxygen atom because it's atomic number 8. Okay. So let's go ahead and pencil in nitrogen. Okay, so there's nitrogen. Now, here's the deal. We are not going to go up to n is equal to 3. It's kind of like, we're going to have to stick here. So it's like if your family grows, the kids eventually have to buddy up.
First box.
First box. And actually it could go, exactly. It could go in any of the 3 degenerate orbitals. But you're right. It's got to buddy up. Okay, and not only buddy up, but it has to have an opposite spin. Very good. There's oxygen. So fluorine, not so surprising. We can build on oxygen. Okay, so we're revisiting it. How many people think it's going to go fit in one of these boxes? Me too, exactly, with an opposite spin. You got it. Uh-huh.
Oh, wait. When you say we're not going to go to the 3, do you just add boxes when you need them, or?
So the boxes need to be according to, The boxes need to be according to the rules that we talked about on Wednesday. The fact that, you know, S's have 1 box, P's have 3 boxes. So you can't just add a box because it's a 2P.
Okay.
You can't build on an addition, another home or anything like that.
Okay.
Yeah.
I was getting a little confused on how you're getting the boxes.
Yep, the boxes are set in stone as S, P, D, and F as 1 box, 3 boxes, 5 boxes, and 7 boxes respectively. But now the one thing I need to come back and revisit is how do you know which subshell to go to next? And that's the one thing we talked about earlier this morning. It's according to its N plus L value of the subshell. And we're going to use the arrow diagram. Okay, all right. So neon, what do you think? What, does it look special? It is special. Okay. It is special. So actually, a little bit in this, maybe Friday, and a little bit in this unit, but more in the next unit, we're going to be talking about ions and basically atoms losing electrons or gaining electrons. And as some of you who have dabbled in chemistry, we're all dabbling in chemistry, if you ask me, okay? If you've dabbled in chemistry before, you've heard about this complete set of 8. Sometimes it's called an octet. Okay, and the set of 8 sometimes is called NS2, NP6. Okay, where, okay, the 2 electrons in an S-type subshell, 6 electrons in a P-type subshell adds up to 8. That's a complete octet. And neon is in a family, and you're supposed to know the family's name over there, right? Okay, the rare gases, noble gases, inert gases, name of that family. They are already happy. All right. So let's visit those same elements and let's use the non-hand cramped method. Okay. So we're going to write the subshell, and then we're going to use these little superscripts in the upper right-hand corner of the subshell to say how many electrons there are. So now, it's the easy way. It's the streamlined, non-cramp hand way called spectroscopic notation to say how electrons are configured. We're going to focus on basically the order how electrons are added, but you can also kind of rearrange it after you come up with it in the order of, that's order filling, order of increasing n. So anyway, without further ado, you know, hydrogen has 1 electron. We said it's going to be in the 1s subshell. So that superscript 1 is that electron. Okay. Helium has 2 electrons. And we said that they're both going to go in the 1s, so that means we have to have a superscript 2. And so when I get to rattling these off, you'll hear me say this is 1s2. So 1s is the subshell, and 2 is the number of electrons there. So the box and arrow notation of lithium, we said now we need to go into n is equal to 2. So we need only 1 electron in that last 2s subshell. So it's 1s2, 2s1. And since those superscripts are the number of electrons, if you ever get lost, like I do sometimes, if you ever get lost and need to know how many electrons you've accounted for, just add these up. So basically, we have 3 electrons represented there. So the next one is beryllium. We're going to add another electron to our 2s subshell. So it's 2s2, it's 1s2, 2s2. So again, when I start to rattle them off, the first number is the n, and then the orbital type, and then the last number is the number of electrons there. Okay, so atomic number, that's 4. Atomic number 5 is boron. And it's 1s2, 2s2, 2p1. I almost feel like I'm playing bingo sometimes. Bingo! Carbon, 6 electrons. And we got all excited, or I did anyway, because we got to show kind of how those electrons spread out in the 3 degenerate orbitals of 2p. But I mentioned that it seems like you lose a little bit of information here with the spectroscopic notation, because we're not really showing Hund's rule.
Because it kind of still looks like they're paired that way.
Yeah, it just looks like we don't know the details exactly. So it's 1s2, 2s2, 2p2. Again, if you add the superscripts, 2 plus 2 plus 2, we get 6. And so actually 6 electrons, atomic number 6 protons, we're right on track there. Nitrogen has 7 electrons, so it's 1s2, 2s2, 2p3. But see how these just seem a lot simpler to write instead of the box and arrow.
I could see this cramping your hand, though.
That's true, especially if you're like, oh, I just know it, I just want to get it down on paper. Yeah.
Yeah. Like if you're doing like unium,
Yeah, that's true.
which has like 200.
But there's something called a rare gas notation that we definitely would use for that one. Or yeah, abbreviated rare gas
Trying
notation.
to do this for unium.
So oxygen has 8 electrons, and they are configured this way: 1s2, 2s2, 2p4, sharing a room, right? We know when we did the box arrow notation. And then before we get to the rare gas, we have 1s2, 2s2, 2p5 for fluorine. And then finally, last but not least, we get to the 10 electrons around a neon atom. 1s2, 2s2, 2p6. And again, 10 electrons, yeah, that's 2 plus 2 plus 6. That is 10. So that all works pretty good. Okay, all right. So one of the things I still need to talk about is the arrow diagram. So I said basically if you're a visual person, I said basically we're going to start to load these low energy subshells, and then the next low energy subshell, and the next low energy subshell. And the only way you can know the order, or I think the best way, is this arrow diagram. Okay, it will have things kind of shake out with regard to their lowest n plus L value of a subshell. So in order to prepare the arrow diagram, which a lot of times I make this on my test, this is going to, let's just say it, this is going to be a test question, okay? A week from tomorrow, you're going to have a little space before you do your electron configurations for you to draw this arrow diagram. Whether you use it or not, that's up to you. But you're going to recognize these subshells. So we start with n is equal to 1. There's only one subshell, so that's our first row. And then we go on to n is equal to 2. Now, alignment is important. So can you see where I put the 2s right under the 1s? But now I get to, on the same row, put a 2p. Not so surprising, when n is equal to 3, I have 3s, 3p, 3d. Okay, I have a third column. When n is equal to 4, okay, I'm lining up my s's, my p's, and my d's, and my f. Now I just have an f. So now you need to do this all the way up to n is equal to 7. So here's the deal. Remember, we don't have any G and H's. No G and H's subshells when electrons are in their ground state. So when n is equal to 5, I'm going to stop at 5f. When n is equal to 6, I'm going to stop at 6f. When n is equal to 7, I'm going to stop at 7f. Okay, so these are all subshells. And don't worry about these kind of grayed out guys over here. All right, so those are subshells. The arrow part of the arrow diagram comes like this, and they are diagonals. Okay, so here's our first diagonal. And we're actually going to see the significance of a diagonal, these blue lines, is that they go along and pick up subshells that have the same n plus L value. So 1s, n plus L. See, 1s, n is 1. If s, that's 0, right? So 1 plus 0 is 1. Its n plus L value is 1. Okay? The first two diagonals are the most boring. Okay? The first two diagonals only pick up one subshell. The n plus L value of 2s is 2. Okay? We said a few times ago. Now, we said the n plus L value of 2p and 3s are both 3. So here's the deal, though. When we start to use these diagonals, these blue lines, we're going to start at the top of the blue line and go down towards kind of like the tip of the arrow shows. So the next diagonal only picks up 2. And if you've kind of misshapen your rows and columns when you drew these subshells, your arrows don't go like they're supposed to. Your diagonals don't work right. So 3p and 4s both have an n plus L value of 4. Now it gets really exciting. I get to pick up, can you see the three subshells? Okay, 3d, 4p, and 4s all have an n plus L value of 5. The next one, n plus L value of 6, n plus L value of 7, n plus L value of 8, okay, 9, 10. Okay, so those diagonals are all basically the same n plus subshells with the same n plus L value. Again, we're always going to start at the top of a diagonal, go down.
So is 6G also 10?
Yes,
Okay.
it would be. That's how that works.
The ones that we're ignoring.
Yeah, we don't need
Evil.
we won't be using them as electrons are in their ground state. And sometimes students, I don't know if this will help you or not, but I thought it's kind of clever. I've seen students at the top of all of the S's. Let's see, I think I'll pick on purple. At the top of all the S's, I've seen sometimes students put 2 electrons, okay? And the top of all the P's, how many electrons can P's accommodate? 6, yep. You know, it's a thought. On top of all the D's, how many electrons? Yep, 10 electrons. And the F's, yep, 14 electrons. Okay, but that might make it, I don't know, confusing. Okay. So here's a figure from your textbook doing basically the same thing. I like my arrow diagram a little better. It has the ones missing that you won't need to use also, but. Okay, so there's an arrow diagram up here. This is your friend. You're going to need to do this for your Unit 2 exam. So let's go ahead and kind of use the arrow diagram and find homes for the 19 electrons around a potassium atom. Okay, I'll show you how this works. So we're going to use the first diagonal. It's kind of boring. The first 2 diagonals are pretty boring. First diagonal picks up 1 subshell. And notice that it's 1s, and I said we're going to max out with 2 electrons. So 1s2 is I'm on my way. We skip on to the second diagonal. Okay. With the second diagonal, it's the orbital is 2s. Excuse me, not orbital. The subshell is 2s, and it has 1 orbital, but anyway, it can accommodate 2 electrons because it's s, so it's 2s2. Now I go to the top of the arrow. I go to the 2p, and I can accommodate 6 electrons, and I'm going to have to use all of those rooms, okay? Because right now, and I do this a lot, I kind of add up my superscripts. Right now I'm at 10, and I need 19. So continuing on that same diagonal, I go to the 3s. So after 2p6, it's 3s2. Now, looking at my arrow diagram, I'm ready to go on to the third diagonal. The top of the third diagonal is 3p. Okay, so it looks like I have 10 plus 2. I have 12 electrons. I need to go ahead and I definitely have room to totally fill that 3p with 6. So I've got 10, I've got 18 electrons. This actually is a very good example. A lot of times students will just want to do what I did right here. They'll want to basically go to the 3D subshell next, but you don't do that. Notice where we need to go next is continue on that diagonal. 4s, and I told you, I kind of told a lie up there. The 4s subshell actually has a lower energy than the 3D. It does. Sometimes you're like, prove it. I'm like, oh man. Let's go find a research lab somewhere. No. Okay, it just does. Okay, so that was my unscrambling part of this board. So can you see then, when I go ahead and put 1 electron in that 4s subshell, if I were to add 2 plus 2 plus 6, that's 10, okay? And add add that to this 8, that's 18, and add that to that 1, 19. Yes. Yay. Okay.
Oh dear.
Whew.
Oh dear.
Oh, I'll be driving down the road too.
Okay, so we ready for the next one? 40 electrons. Okay. I'll just kind of streamline this a little bit. How's that? So the first diagonal only picks up one subshell. It's the 1s, and we max out at 2. So 1s2. The second arrow picks up one subshell, and it's 2s, and we max out at 2. So 2s2. Then we go on to the third arrow, and we start with the 2p and then go to the 3s. And I think we're going to have to go ahead and fill both of those. Okay. Notice for potassium and now for zirconium, I have these little drop-down boxes when we reach a group 8A element, when we reach a rare gas. Okay, that's actually significant. So we have a rare gas there with 10 electrons, neon. All right, so now we're going to completely fill that 3s, it'll be 3s2. On to the fourth arrow, starting with 3p. We're going to go 3p6. I guess the other thing I should note is that your p's are pretty special too. When you totally fill a p subshell, you know, like p6, if you look back, there's a good chance that you have basically reached a rare gas electron configuration. And 18 electrons, just like this, is how argon has its electrons. Okay, argon is right under neon. Okay. So it looks like we're ready to continue. This is where I said I need to scramble and put the 4s, insert it energy-wise a little above the 3p and underneath the 3d. Okay, so we're going to put 2 electrons in the 4s. Now we're ready for the next diagonal. The next diagonal has 3 subshells, 3d, 4p, and 4s, and that's how they roll. So let's see. 3d, 4p, that's fine if I move that one down, and 5s. So here's where actually
5s is
Yeah.
deeper than
5s goes right there. Okay. So let's go ahead and see what we need. So how many electrons are going to be in that 3d? If we fill it up, how many electrons can a D-type subshell accommodate?
Isn't it
10. It is 10. So you think we need homes for 10 more? So that's 18 plus 2, that's 20, plus 10 would bring us up to 30. Yeah. So yeah, you know, exactly. So we're at 30 there, on our way to 40. So what do you think? Are we going to go ahead and fill that 4p subshell with 6 electrons? Yep. Anytime you have a p superscript 6, you should be thinking, I bet I just hit the end of a row, a period. And you did. That's actually krypton. I love krypton. Okay. So if you add up all of these little superscripts, you're at 36 electrons. So we only need 4 more electrons. It looks like next on our arrow diagram, next stop is 5s. Are we going to fill it?
Yep.
Yep, 5s2. Okay, we only need 2 more electrons. See, now this is a good example, and I'm going to actually show you on Friday an alternative way of just glancing at the periodic table and kind of knowing. But this is a good example of, I'd be like, I don't know where I go after 5s, but if I look at I'm ready to begin a new arrow. Okay, 4d, and how many electrons? 2. 2. 4d2. Whew. All right. Any questions? And it gets, sometimes students are like, well, that doesn't look as pretty as if I just did it like this over here. But this isn't the way electron energy levels are. This is. Okay? So, now, here's the deal. I mentioned that there is, you know, if you get up to like a zillion electrons, this could be turned into hand cramp. But the cool thing about this is actually there's something called the abbreviated rare gas notation, where basically you stop the last rare gas. Rare gas, remember, is the 8A. So the last rare gas we had was krypton. Basically, you put krypton in brackets, and you have done all of this. So all you got to do is do brackets krypton minus 242. Got it. Okay. So that's an alternative. So sometimes, and I'll tell you, actually we'll get to this on Friday, sometimes it's convenient, or there'll be times when you want to make it pretty. Basically kind of unscramble your end, put your ends together, increasing end. So this is how those 40 electrons are configured in what we call the order of adding. And this is actually kind of unscrambling it, moving your 3 over, getting your 4s together, moving your 5 out, however you want to say it. It's the same electron configuration. I don't require that you necessarily ever do this, unscramble it, but it can be helpful. Okay. So yeah, you're like, really? So I think what we're going to do, and I kind of wish I'd gotten to give you an assignment today, but instead of giving you an assignment today, I'm going to hit you hard on Friday. But one thing before we go, I want to emphasize this, what we're going to hit on Friday. We could go ahead and write the same configuration, okay, using the abbreviated rare gas notation. What I told you is, in this case, it would be brackets KR, and then what is after KR? 5S2, 4D2. Whoops, goodness. 5S2, 4D2. Okay, and we're going to do that for IDing on Friday, first thing. All right? No homework assignment given today.